Anyone else have any ideas? Here's some of what I'll be talking about today. We enhance those images to be able to see those details a little more clearly. We can get better resolution on those images. We'll have some more astrophysical, scientific motivations, and we can also represent things that we don't actually see. So going back to the Neptune controversy, on the left you see a little screen grab that I got from C-SPAN. There's all kinds of archives on C-SPAN, including the press release from 1989 where they first showed these images from Neptune from the Voyager 2 spacecraft. And they talk about how they've enhanced the image on the right, on that left-hand image, but on the left you actually have the real image. But the reason we know the image more on the right and this little inset one is because when they gave those images out to the press, well, they could only print out one color image because color images were really expensive back then to distribute. So are you going to distribute the one that doesn't look so good or the one that actually shows all the detail that you see on the surface of the planet? To quote the leader of the imaging team, the enhancement is necessary to bring out the detail. And this is the detail that he was talking about at the time, the Neptune's great dark spot, about the size of Earth, and those white regions that you see are very high altitude cirrus clouds that we also see on Earth. Except on Earth, we get the cirrus clouds because of frozen water. This is actually frozen methane. And the dark spot is because of the gap in the methane clouds. So this, if you didn't enhance this, you wouldn't be able to measure this really well. You wouldn't be able to understand it as well as we could. And just wouldn't be able to see it. And also astronomers just really want to be Harrison Ford from Blade Runner. Another reason why we do this kind of imaging is because we want to get more resolution. So if you, I'm assuming most people grew up with cathode ray tube television here. I definitely did. If you look really close, like if you got really in front of the screen, you would be able to pick out all those little different color pixels, right? And that's how we see images on screens nowadays. It's just a mixture of red, green, and blue pixels. That's how we also take photos on cameras. So you have these red, green, and blue pixels that are absorbing the light. But you're only capturing a third of that resolution in each of those pixels. So what astronomers usually do is just have black and white pixels. So you can get more of that resolution. You get 3 times more resolution on all those images. So this is a photograph from JWST. I believe it was on Sunday. I found it online of the galaxy NGC 2775. Just look at all the detail in the disk. It is really beautiful, and it just shows astronomers where all the structures, all the dust lanes in that galaxy, where stars are being formed, and it's really exciting to be able to study stuff like that. But what color is this? So the way we choose how to color our images, or in which filters that we want to use, is by using all these different filters on the left-hand side. So this is the filter color wheel from the JWST telescope. And these, on the right-hand side, is the diagram of all the different colors that this color wheel can let through and be able to pass onto those black and white detectors. So on the top, you have a wideband filter. So it lets in a lot of color across different wavelengths. So it's kind of like our eyes. We can see yellows, green, reds at once. But on the bottom, you see these really small peaks where the filter is only letting in very specific wavelengths of light. So maybe that filter down over here is only letting in a very specific color of red. And we call these narrowband filters. And there's different scientific reasons why you want to do this. So the filters on the top, those wideband that let in all those different colors of light, you might want to just take a normal photo of a galaxy, something that we might be able to see with our own eyes. On the bottom, using those narrowband filters, you might want to be able to detect what kind of gases that are in whatever you're imaging. So when a gas that is low density is heated up, it will emit very specific colors of light. It's like a little, like a barcode. I live right next to the train tracks, and the train's always scared now. So yeah, those barcodes of light tell us what element, what gases, what molecules that we're seeing in all those different galaxy structures that we're seeing, or all those nebulae. So if we're able to use a narrowband filter, we'll be able to pick out very specific molecules being emitted. And this is what that kind of imaging looks like in all those different filters. This is from, I think it was from the Hubble telescope. So you see in the bottom right, we have this very red filter, an infrared filter that we're using. So that picks up all of the dust and hydrogen that's in this galaxy. We filter around to say like the green. We see all the stars that are being, that are all shining, they're all heating up the gas and the dust surrounding the stars. And then on the bottom left, in the ultraviolet, we have these high energy regions where the stars are really shining bright and also heating up that gas to really high temperatures. And then you can combine these all to create this one really beautiful picture right in the middle. So on the left, we have an image of what you would actually see with the eyes from the Hubble Space Telescope of, I can't remember which galaxy or which nebula this is, but you can see it's mostly red, and this is coming from dust and from hydrogen gases, which is beautiful in its own way. But if you want to really understand the structure of this nebulae and all the gases that are forming new stars in the stellar nursery, you really want to pick out the oxygen and the sulfur, amongst other elements, and then assign them a specific color. So in this image on the right, sulfur has been assigned red and oxygen has been assigned blue. I think they removed the hydrogen that they were detect, and you can really see how those two gases are interacting with each other. And this is really important for astrophysicists because most of the universe is made from hydrogen and helium, mostly hydrogen. But these higher mass molecules and atoms and gases were formed in the centers of stars. And they later formed planets like Earth. And this is how life began. This is what Carl Sagan meant by "we are literally stardust," because we can see these signatures of sulfur and oxygen. Here's another image I really like. This is from 3 different telescopes looking at different wavelengths of light that we can't actually detect. So in red, we have the Spitzer telescope imaging in the infrared, Hubble in the near infrared, so we just too red for us to see, and then Chandra in the X-rays. And this is actually the center of our galaxy. So if you have observed the Milky Way using optical light that we can actually see, all you'd see is dust. You wouldn't be able to see much. But with this, with this image, you can actually see a lot more detail. So in the red and bottom, you see all the hydrogen and dust in between all of the spiral arms of our galaxy, and in the middle of our galactic center. In orange, you can see where stars are really heating up those gases. And then in blue, you can see really where the galactic center is, this really high energy region down here. But this is my favorite part of this kind of imaging, or why we do this. This is called the bullet cluster. And in those dashed white lines, in those circles, you see 2 clusters of galaxies. So where 2 groups of galaxies are held together by gravity. won't be able to tell this from this image, but they've actually, well, not collided, but they move past each other, they move through each other. So this galaxy is actually moving this way, or this galaxy group is moving this way, and this galaxy group is moving that way, and in the middle of here, they combined 1 million years ago. And because these galaxies all clump together, we can tell in these blue regions that there must be a lot of mass that are keeping these clusters together. There must be some sort of matter in there that is keeping them together. So that's what the Chandra telescope tried to do a couple of years ago. They tried to image all that matter that was in between those galaxies, and using X-ray telescopes, they found some really some hot gases and dust that interacted with each other when those clusters of galaxies collided with each other and moved past each other. And you can see why it's called a bullet cluster. This looks like a bullet moving through a target. So you've got this little shockwave here, and where where the other cluster was just in its way. But if we superimpose those two images of each other, so in pink we have that hot gas that looked like a bullet, and then blue is where the mass we expect it to be. They don't overlap with each other, which is really interesting. And it doesn't make sense, because we expected that all of that hot gas to be where the blue region is. So there must be some missing matter that we don't actually see. And this is what we call dark matter. There must be something in that blue region that is holding those clusters of galaxies together, but we don't actually observe it electromagnetically or with light. So this is one of the strongest pieces of evidence that we have that dark matter exists. And then finally, another reason we show images of astrophysical stuff that those images may not be real is because they're reflecting actual data that is really abstract. Does anyone understand or know what this would be, what this is trying to represent? Honestly, if I first took a look at that, I wouldn't know either. But what this is actually showing is a donut ring in the sky. Does anyone know what that donut ring could be? It's a black hole. So this is actually multiple simulations that have been averaged over each other, and they would give the same result as that image that that data on the left. And that data was collected by the Event Horizon Telescope a couple of years ago. And both of them agree with each other, and this is why we have this image on the right, and we call it the black hole at the center of galaxy M82. So this might not be real, but this is what we think is there, and it reflects what we're actually seeing, and it's really strong evidence, this is what we believe is to be the black hole at the center of that galaxy. So yeah, this is a very whistle-stop tour on all those different images that you see in the news, in astronomy news, and maybe some documentaries and such. I hope it gives you a bit more context on whenever some news comes out, and whenever someone's trying to debunk what we do and what we work on. Or maybe you still think that I'm lying to you, which might be true as well. But thank you for listening. I'll take any questions.